Okay, let's continue on. So the next lecture we have is 3.3, and 3.3 is on what we call concavity. Okay, so concavity is another thing about the graph that we're going to look at. So before we even get into any calculus or anything behind that, let's just look at a graph and discuss the concavity. Okay, so let's say that that's what our graph looks like. So hopefully we can agree that we have some relative mins and relative maxes going on. But that's not so much what we're focused on in this section. So concavity means the shape of the graph. And the shape of the graph means, is it making like a bowl or an umbrella, okay? So that's the concavity. What's the shape of the graph? And we say that a graph is concave up if it looks like a bowl, so if it could hold water, okay? So concave up, most definitely. Concave down means that it's gonna look like an umbrella, okay? Or the water is going to fall off. So we've got definitely concave down and concave up. And so that's what we're looking at here, is not so much the mins and the maxes. We're not interested in that. We're interested in where the concavity changes. So the idea is this whole side of the graph is concave down. Would you agree? Until we reach maybe about that point. So as we come down over that, there's a point where the concavity goes from being an umbrella to being a bowl. Okay, so this over on this side would be concave down. And this maybe till about there. You know, again, it's just my graph there. So this part right here looks like a bowl, so this part is concave up. And then once we get here, notice how it goes back down again. Now, it didn't make the full umbrella, did it? But it's still, it's not collecting water, is it? Water's rolling off the back here. So this would be concave down again. Okay, so the concavity is also a very important part of the graph. And for us in business, it does have its purposes, so we'll talk about that in a minute. But we just want to talk about how do we figure out, if you don't know what the graph looks like, how do we figure out about the concavity, okay? And before we do get into that, just one more other thing here. These two little points here, where the concavity changes, those are called inflection points. So we'll make a little definition there. So we'll say an inflection point is the point on the graph where concavity changes. Okay, now remember that when we look at the first derivative, the first derivative can tell us where we have minimums and maximums and where we are increasing and decreasing. So if we want to then talk about concavity, when we want to look at concavity, it means we need to go one step further and we need to go to the second derivative, okay? So we're going to use the second derivative. We're going to find critical values, but this time these critical values are going to be these inflection points. They're not maxes and mins, they're inflection points. And then we can find intervals of concavity. So it's basically doing exactly the same thing that we did in 3.1 and 3.2, but with the second derivative, and the second derivative will tell us whether we are concave down or concave up, okay? So that's what we're looking at here. Okie dokie, so let me give us an example here. Where's my example? So this says f of x equals 12 over x squared plus 4. And then this time it's just going to say something like discuss concavity. Now remember, when it says discuss concavity, All that really means is to make the little table with the little intervals, and that's it, okay? Okay, so if we need to find the derivative of this guy, we could use the quotient rule, but as the top is just a constant, I think I'm just gonna flip this guy up to the top. So I'm just gonna rewrite here as 12 and then x squared plus 4 to the negative 1. Okay, so just rewrite it. Okay, so let's go for the first derivative there. So if we find the first derivative, the 12 just comes along for the ride, but we're going to bring down that negative 1, so we'll have negative 12 x squared plus 4 to the negative 2. And then the derivative of the inside, don't forget the derivative of the inside, is 2x. Now, we're not done with this guy. We got to go one further, so let's simplify a little bit here. So we're going to have negative 24x and then x squared plus 4 to the negative 2. Now, the unfortunate thing about this is because of that doinky little x there, we now have to use the product rule. Yippee, right? So, let's see what we got here. Or we could put that guy back down in the bottom and use the quotient rule. Want to try that? Let's do that instead. So negative 24x, x squared plus 4 all squared. Okay, so one more time, and I didn't leave myself enough space, so I'll erase this. We'll come over here. So now we're going f double prime of x. All right, so we're using the quotient rule, so we're going to go low d high. So x squared plus 4 squared. The derivative of the high is just negative 24. Minus high, negative 24x. Okay. D low, which will be bring down the 2, x squared plus 4. And then inside is 2x, right? New exponent is 1. And then all of this over x squared plus 4. Now this is to the 4th power, right? No one said these were easy, okay? So these functions, when you get to that second derivative, they're not always the prettiest looking things in the world. So we have some work to do on this. We definitely don't want to leave it like that. So one thing that we can notice, do we notice that in each term, so there's one term, there's the other term, each term has an x squared plus 4 in it. So could we cancel out a single x squared plus 4 with one of the x squareds plus 4 in the bottom and put that as a 3? So now we're left with up top x squared plus 4 times negative 24, I'm going to just combine those two, plus 24x times 2 times 2x, all over x squared plus 4 to the 3rd. Okay, so let's see what we got here when we put everything together. So we have negative 24x squared minus 96. Plus 496 x squared all over x squared plus 4 cubed. Phew, okay. So it was tedious, but at least we got it down to something nicer. I guess we could go even further there. So the 96 minus 24 is going to leave us 72x squared. Who the heck came up with this problem? Minus 96 all over x squared plus 4 cubed. All right, so that's as easy as it's going to get. Okay, now we're going to look for these critical values, but this time, remember, this is going to be inflection points, not minimums and maximums. So find the critical values. Now remember, we're always supposed to look at the denominator, but notice in this denominator, is there anywhere that this could ever equal 0 or even be negative? There's not, is there? So we actually don't care about the denominator. So it's not affecting us at all. So what we really need to do is just 72x squared minus 96 equals 0. Okay, so x squared equals 96 over 72. 96 divided by 72. That is going to be, I don't want to do this. Or we'll just do it in decimal. So that is going to be 1.33333, a bunch of threes, and then we need to make the square root of that. Square root. No, stupid square root. Square root. Okay, so I've got x is equal to plus or minus, don't forget the plus or minus, 1.15. Okay. Look good? Probably not. It's a mess. Yes, it most definitely is. But that's why we have practiced our derivatives so that when it finally comes to one like this, we can actually go ahead and work it through. Now, the problem is that we're not even done with the frickin' problem yet, right? Okay, we haven't even gotten there. So now what we need to do is make our little table, interval, second derivative, and then over here is going to be concavity. So remember the plus and minus sign, so we're going to go from negative infinity up to the negative 1.15. Then we're going to go from negative 1.15 to positive 1.15. Then we are going to go from 1.15 to positive infinity. Okay. Now, remember that we're only interested in whether it's going to be positive or negative. Oh, wait a minute. It just occurred to me, shoot, that I forgot to tell you that when it's positive, it's concave up, and it's negative, it's concave down. So let's do this problem, and then we'll write that on the board. I apologize. It wasn't in my notes. That was so dumb. This is what happens when you don't take thorough notes. So I apologize, you guys, but it's really not that bad. Okay. So let's take a number out of this, like -2. And remember, all we're interested in is whether it's negative or positive. Okay, negative or positive. And we know that the bottom is always positive, so we really don't care about it at all. So we just want to know what happens up here. So if you plug in -2 there, that's going to be a positive 4, right? Times 72 is a really big number, minus 96. Can we agree that this is going to be positive? Now, number in this interval, nicest number that's in this interval is 0. Go with 0. If we plug 0 in here, remember, don't worry about the bottom. It's going to be a negative 96, or just negative. Okay. And then one more time, put in 2, 3, 4, whatever you want. If you put in 2 there, that's going to be 4 times 72, and then minus. So this is actually going to be positive again. Okay. All right. Now, like I said, we were able to do this point, but then I forgot to tell you about the concavity test. So, concavity test. So this says, if f double prime of x, okay, is positive on a to b, f of x is concave up on a to b. And the second part says, if f double prime of x is negative on a to b, regular f of x is concave down on a to b. Okay. So I apologize for that. That should have been there at the beginning, but at least it's there now. So we're working on our table here. We've discovered where the derivative is positive and then negative and positive. So when this says that it is positive, that means that we are concave up. Then we're going to go concave down. and then we're going to be back to a concave up. Okay, so that's how we use the second derivative to look at concavity. Now, in our case, for business applications, we're not really worried where every single graph is concave up or concave down or inflection points, but it does have our one main purpose. Okay, so in business calc, concavity comes down to what we call the point of diminishing returns. So as an example, let's see. So in a business application, we might see a graph that looks something like this. Okay, so it's not a whole XY graph because we're definitely going to start at 0, 0 because it's a business application. But what we want to be able to understand is how does this affect us as in a business sense. So first off, this is not as clear as before, but can we tell that here, do you see how you have kind of the start of a bowl here, and up here you have kind of the start of the umbrella? So this point here is our inflection point. Okay, but that point now is going to be called the point of diminishing return. Or point of diminishing returns. Okay, so what happens is when you're looking at a business application and you're looking at a graph that is concave up means that you're seeing more growth than what you've put into it. So however much you're putting in, you're getting more growth out. So you're getting more bang for your buck. The more you put in, the more you get out. And that will always give you that concave up shape. Okay, so the idea is if you were to put in $1, you're gonna make more than $1. That's kind of the sense there. Whenever you see that concave up, you put in money or you put in whatever, you're gonna get more bang for your buck, okay? But then there becomes a point where the inflection point happens and the graph turns to concave down. And once it's concave down, now it doesn't mean you're not making money or anything, but what happens is you're not getting as much bang for your buck. So if you put in $1, you still might be making money, but you're not making as much as you were. So your profit is still increasing, but not as much as it could have been. So this would have been like the point to stop, because the more you put in, you're getting more out. Once you get to this point, you might still be making profit, but it's not coming in as fast. Okay, so we want to know where to stop. Okay, so again, we'll make just a little note of that. We'll say concave up. Means each additional dollar returns more than the dollar before. Okay. So you say I'm going to put in another $1, and you're getting more out of it. You're getting more profit or more return out of it. Okay. Concave down means each additional dollar returns less than the dollar before. So again, like I said, you might still be making a good profit, but you're not getting quite as much bang for your buck. So you're not losing money. It's just that compared to what you were doing before, you're just not making it as fast, okay? So that's how the concavity affects us. So in most cases then, we want to maximize our returns. So that's where we're gonna look for the point of diminishing return, and that's gonna kind of tell us where to stop. Even though we could continue to make more money, there's a point where we go, you know what? Maybe this is the best place to stop. So let me look for our example here. No, where's the example? Okay, here we go. So this says, by increasing advertising costs, X in thousands of dollars, a company discovers they increase sales Y in thousands of dollars according to Y equals negative 1/10 x cubed plus 6x squared plus 400, and then this says from 0 to 40. Now remember, all of these numbers are in thousands, so that's 0 to 40,000, but we're just using it in that term right now. Okay, so then it says find the point of diminishing return. Okie dokie. So this is what we're looking at. So in this example, they're increasing advertising. Well, we know that if you advertise your product, you're going to get people to buy it. Okay, so that's that's common. But the thing in this example is that there comes a point where you could keep throwing more money into your advertising, and yeah, there'd be more advertising out there, and you might still make profit, but you're not going to get as big a bang for your buck. Okay, so your profit might continue to increase, but not as much as if you stopped at a certain point. So if we want that increase to be just at the right point, what we're going to look for is the point of diminishing returns. Now on this one, they're also saying that they have money for advertising, but they're not going past $40,000, so the 40. So, this isn't like, oh, we can advertise forever and ever. The advertising needs to fall somewhere between $0 and $40,000. So if we want the point of diminishing returns, that's looking at the second derivative. All right, so we got to go through this twice. So let's find y prime first. So y prime will be negative 3/10 x squared plus 12x. Oh, that's it. Okay, that's not bad. Okay. All right, but we need the second, right? We don't need the first. So this time we'll bring down the 2, so that'll be negative 6/10 x plus 12. And as we're in a business application here, why don't we just go like that? Still decimals, right? So we've got negative 0.6x plus 12. And in order to find the point of diminishing returns, we're going to take this second derivative and set it equal to 0. Okay? So we will end up with x equals 12 over 0.6. And again, I'm pretty sure that's 20, but you know, with decimals, it never hurts to try. 20. Okay, my math has not failed me. So we get x equals 20. Okay? So the point of diminishing return is going to come when x equals 20. But now remember, is this $20? Is that what you're putting into this? Or is it 20,000? So even though the answer said 20, don't forget to add the thousands, put the units on there. Okay, so how much should they put into advertising? $20,000 will maximize the profit as opposed to how much money you put in there. Okay, so we're going to make the biggest bang for our buck if we invest $20,000. Right? Okay, look good? Okay, so there's a couple concavity problems where you look for concave up and concave down and that type of thing. But the most of it we're interested in is this point of diminishing returns. This is how the second derivative really applies in a business application. Okay, guys, that's another lecture down. All right, see you next time.